Okay, so ready to dive in today.
Always. What do we have?
Let's talk enzymes.
Okay.
Like, not just regular enzyme stuff.
All right.
This is next level stuff.
I'm intrigued. Lay it on me.
This is about how we can use AI and machine learning to build better enzymes. Like, imagine designing these little protein machines that make life work.
Right.
With incredible precision.
Yeah.
Like, you could tweak them to do exactly what we want.
It's pretty amazing stuff.
Yeah.
It's like we're taking this field that's always been about tinkering, about slow, careful changes.
Right. It's been a real bottleneck.
Totally. And suddenly it's like we're handing scientists this way to make these huge leaps forward.
It's crazy. And just a reminder to everyone listening, we're talking about enzymes, those workhorses of the biological world, breaking down food, building new molecules. They're involved in everything.
They really are.
And we care about engineering them because, well, they hold the key to some really game-changing stuff.
Yeah, like what?
Biofuels.
Okay.
New medicines. Even like materials that could change how we build things.
Totally.
But getting them to do what we want.
Yeah.
That's been the tricky part.
Yeah, it has been. It's been a bit like trying to solve this giant, crazy, complex jigsaw puzzle.
Oh, like that.
In a dim room. You keep trying different pieces. You make a little bit of progress, but it's slow and it's painstaking.
It's so inefficient.
Yeah.
And so this is where machine learning comes in, right?
Exactly.
Floodlights are on. We can actually see what we're doing now.
Yeah. And the thing is, what's incredible is the sheer volume of data that we have in this field now. We're talking protein sequences, we're talking structures, years and years of experimental results.
It's overwhelming.
It's a lot. And humans are good, but we're just not built to process information on that scale.
Yeah.
Machine learning, though.
Yeah.
It eats that stuff up.
It thrives on it.
It thrives on it. It's like we handed it all the blueprints to, like, life's machinery.
Right.
And we said, go on, figure it out.
Yeah.
And it's figuring it out.
It's amazing. And there are two key players in this game. Right? So we've got supervised learning and unsupervised learning.
Right.
So let's start with supervised.
Okay.
Imagine you're teaching a dog a trick.
Right.
Right. So you show what to do.
Yeah.
You reward it when it gets it right, and eventually it learns.
Yeah.
So supervised learning is kind of similar. We're feeding the algorithm tons of labeled data.
Right.
For example, which mutations in an enzyme make it more stable?
Okay.
And which ones make it, fall apart?
That's a really good way to put it. Yeah.
And one of the papers we're looking at, the one by Kuba and the team, highlights this example of supervised learning called PON-STAB.
Yeah.
And it's designed to predict how mutations, those tiny changes in the protein sequence, will impact an enzyme's stability.
Because we want stable enzymes.
Right, because a stable enzyme is a happy enzyme, which means it can actually do its job out there in the real world.
For sure.
But I'm guessing predicting stability is not exactly a walk in the park, even for a supercomputer.
You're right. Even PON-STAB, which uses...
Oh, is it over 1,000?
Yeah, over 1,000 different features to analyze each mutation. Wow.
It still has a really tough time with this.
Yeah.
And it just highlights how complex, the dance of molecules is at that level.
Really, really complex. So that's supervised. But then we have unsupervised learning. Right. Which is more like giving the algorithm a big box of Legos.
Okay.
And saying, go wild, show me what you can build.
I like that analogy, yeah. So instead of us looking for a specific answer,
right,
unsupervised learning is all about finding hidden structures in the data.
Right, those patterns.
Yeah, uncovering those aha moments, those unexpected connections that we might have missed otherwise.
And it's not just about making existing enzymes better, right? It's about finding totally new ones.
Yeah.
Ones that could do things we haven't even dreamed of yet.
Exactly, yeah. And this is where things get really, really interesting, really exciting. Okay, so before we get too carried away with the excitement, let's break down what these machine learning methods are actually doing in the lab.
Okay.
Out in the real world of enzyme engineering.
Right.
What are some concrete examples of how this is all shaking out?
Well, one of the most promising areas has got to be enzyme discovery.
Okay.
So imagine you need an enzyme to, let's say, break down plastic pollution in the ocean.
Okay.
Yeah. Traditionally, you'd be, searching for a needle in a haystack.
Right.
But with machine learning, it's like having a metal detector, right?
Right.
We can use these algorithms to sift through these massive databases of protein information, things like,
Like Brenda.
Yeah, Brenda, Uniprot KB,
Right.
which are these giant libraries of all this protein knowledge. And so instead of blindly testing thousands of enzymes, we can use machine learning to just pinpoint the ones that are most likely to have the activity that we're looking for.
Well, way less time, way less money wasted.
Absolutely.
Much higher chance of actually finding what we need.
Exactly.
That's awesome.
Talk about a win-win.
Huge, yeah. Okay, what else? There's got to be more.
Oh, yeah, there's more. So machine learning is also being used to what we call rationally designed mutations.
So we're getting strategic about it instead of just...
Yeah, instead of randomly tweaking things and hoping for the best.
Right.
We can actually be really strategic about it. There's a...
Is there a tool?
Yeah, there's a tool mentioned in the Kuba paper called the FuncLib web server.
Okay.
And it uses evolutionary information and all these sophisticated energy calculations to predict which mutations are most likely to make an enzyme more stable or more efficient at doing whatever it's supposed to do.
It's like having a roadmap for enzyme improvement.
Exactly.
Instead of just wandering around aimlessly in the dark.
Exactly.
You've got directions. I love it. Okay, what else? Give me more.
All right, so another area where machine learning is having a big impact is something called smart library design.
Okay.
So in the world of enzyme engineering, directed evolution experiments are a big deal.
Right, because it's like speeding up evolution in the lab.
Yeah, exactly. You make a bunch of variations of an enzyme and you see which ones are the fittest.
Right, survival of the fittest.
Exactly.
But the problem with that is those libraries can be huge.
They're huge. It's like...
It's a needle in a haystack all over again.
Exactly.
So how does machine learning help?
So what machine learning allows us to do is design smaller, much more focused libraries.
Okay.
So it significantly speeds up the process.
So instead of a haystack, we're down to like a shoebox.
Maybe even smaller, like a sock drawer.
A sock drawer. I love it. That's a great visual.
And one of the most promising approaches is something called FTMLDE.
Catchy.
Yeah. Well, it stands for Focused Training Machine Learning Assisted Directed Evolution.
Okay, so it does exactly what it says on the tin.
It does. And it combines both supervised and unsupervised learning to basically cherry pick the most promising mutations.
Oh, wow.
And it makes the whole process incredibly efficient.
So we got smarter discovery, smarter design, smarter evolution.
We do.
Feels like we're on the verge of something huge here.
We really are.
But surely it can't all be smooth sailing, right?
Of course not. Of course not.
What about the challenges?
Yeah.
What about the roadblocks in this brave new world of enzyme engineering?
Yeah, we should probably talk about that.
We'll delve into those right after the break. We're back, and before the break, we were getting seriously hyped about all this machine learning.
It's exciting.
And how it can, like, totally revolutionize enzyme engineering.
Yeah.
But, as with anything you know,
sure,
there can be some growing pains.
Yeah.
So let's talk about the challenges.
Okay.
What are some of the hurdles that scientists are facing in this brave new world of AI-driven enzyme design?
Well, you know, one of the biggest ones, it always comes back to data.
Of course. Yeah.
Which shouldn't be a surprise.
Garbage in, garbage out, right?
Exactly.
You can't make a good cake with bad eggs.
Well, that's true, too, yeah.
Or like with a recipe that's got coffee stains on it.
Right, and some of the pages are ripped out.
Exactly.
You might end up with something that resembles a cake.
Maybe.
But it's not going to be good.
No.
And so we need massive, massive data sets to train these algorithms properly. And those data sets need to be accurate. They need to be consistent.
Right.
And they need to be comprehensive. If they're not, we risk ending up with predictions that are biased.
Of course, yeah.
Or unreliable.
So data quality is a big one.
It's a huge one.
What else? What are some of the other, like...
Other bumps in the road.
Yeah, the bumps in the road.
So another challenge, and this is a big one, is what we call the black box problem.
Ooh. Okay, that sounds kind of ominous.
It's a little bit ominous.
Tell me more.
So basically, we often don't fully understand why a machine learning model makes the prediction it does.
Okay.
So we can train this really fancy algorithm to predict, let's say, which mutations are going to make an enzyme more stable.
Right.
And it might be amazingly accurate.
Yeah.
But if we don't actually understand the reasoning behind it, it's hard to fully trust those predictions.
Right. You don't know what it's basing it on.
Exactly.
It's like having a GPS. It's like, go left, now go right, now go straight. And it gets you to where you need to be.
Right.
But you have no idea how.
You don't have a map. You don't know why that was the best route.
Exactly.
You just did what you were told.
Yeah, exactly.
Right.
And this lack of transparency, I imagine that makes it really hard to troubleshoot when things go wrong.
It really does.
Because they always go wrong at some point.
Of course, nothing is perfect.
So are researchers just like throwing their hands up in the air about this, or are they actually trying to fix this black box problem?
No, they're definitely working on it.
Okay, good.
Yeah, there's a lot of work being done to develop more interpretable machine learning models, ones that kind of give us a peek inside the box.
Right, so it's like our GPS now can tell us why it's telling us to go a certain way.
Exactly. Like, oh, this is going to avoid a traffic jam, or there's a toll booth on that other road.
I like it.
So we're starting to see some progress in this area, and as those models become more transparent, that's going to increase our trust in their predictions.
Absolutely, that makes sense. Okay, what about other challenges? Anything else we should have on our radar?
Yeah, so another big one is what we call overfitting.
Overfitting. All right, break that down for me. What is overfitting?
All right, so imagine you're studying for a test, right? But instead of actually learning the material, you just memorize the answers to the practice test.
Okay.
You might ace the practice test, but when it comes to the real deal, you're going to be lost.
Yeah, I've been there.
Because you haven't actually learned anything.
It's not a good strategy.
It's not a good strategy. And overfitting in machine learning is kind of similar.
Okay.
It's when an algorithm becomes too tailored to the specific data that it was trained on.
Okay.
And it doesn't generalize well to new data that it hasn't seen before.
So it's memorized the answers it hasn't actually learned.
Exactly. So it might work great on the data it's seen before, but throw it a curveball, throw it something new, and it just falls apart.
So how do you prevent that?
So it's all about finding the right balance in the training process.
Okay.
We need to use techniques that help to prevent this overfitting, things like cross-validation and regularization. And those help make sure that the model is actually learning the underlying principles, not just memorizing.
So it's actually studying the textbook instead of just cramming for the test.
Exactly.
Yeah, I like it.
And the good news is this is an area of very active research.
That's good.
So scientists are constantly developing new and better techniques to prevent overfitting and make these models as good as they can be.
So we've talked about the data challenges, the black box problem, the risk of overfitting.
Yeah, it's a lot to think about.
It feels like kind of a tightrope walk.
It is.
Getting all of this right.
Yeah, it takes really careful planning, rigorous testing, and a healthy dose of skepticism.
Always good to be skeptical, especially with something this new.
Absolutely.
But even with all of these challenges, there's clearly a lot of optimism in the field.
Oh, absolutely.
I mean, we're on the cusp of something really, really transformative here.
Yeah, we are. We're seeing this really cool convergence of powerful technologies and this growing understanding of biological systems.
It's like all of the pieces are starting to come together.
They really are.
So where does all of this take us? What does the future hold for this very exciting field? Let's explore those possibilities right after the break. Welcome back, listeners. It's really been something, huh? This whole machine learning thing.
Oh, for sure.
It's got the potential to totally revolutionize the world of enzymes.
No doubt about it.
But I kind of want to bring this back to, the listener for a second.
Okay.
Because this isn't just something, out there in a lab somewhere.
Right.
This stuff has the potential to affect all of us.
It really does, yeah. And we've talked about some of the applications, like
Right.
breaking down plastics, right? That pollution.
Yeah.
Designing totally new materials.
So cool.
But it goes way beyond that. I mean, imagine, more efficient manufacturing.
Yeah.
Using less energy.
More sustainable.
Yeah. Powered by these custom-designed enzymes.
That we just, whipped up in a computer.
Basically, yeah.
That's amazing.
And then there's, personalized medicine.
Ooh.
Treatments tailored to your own genes.
That's the future right there.
It really is.
That's amazing. What about food?
Oh, food too.
Okay.
I mean, imagine crops that don't die when it doesn't rain.
Drought resistant.
Yeah. Resistant to pests, all thanks to engineered enzymes.
That is wild. It's like we're on the edge of a whole new revolution.
It feels like it, yeah.
But instead of being powered by, coal or oil,
right.
It's going to be powered by biology.
Yeah. And machine learning is the key.
It's unlocking all of this potential.
It really is, yeah.
But, with great power comes great responsibility, as they say.
That's true.
We need to be careful with this.
Oh, absolutely. It's not just about, going full speed ahead.
Right.
We have to make sure we're developing these technologies responsibly.
Thinking about the ethics of it all.
For sure, and making sure that everybody benefits from it.
Yeah, equity, sustainability.
It all matters, yeah. And this is where you come in, dear listener.
Yes. Get involved.
Yeah, because understanding this stuff, that's what empowers you to make good decisions.
It's ask the right questions.
Exactly. Be a part of the conversation.
Because this isn't just something that happens to us.
Right.
This is something we create together.
We do. So next time you're, getting dressed. Or taking your medicine.
Yeah.
Think about those enzymes.
They're everywhere.
They really are working their magic behind the scenes.
And thanks to machine learning,
Yeah.
we're finally starting to figure out how they work.
I know. It's like we're cracking the code.
And that means we can start using them to, shape the world around us.
It's a journey, that's for sure.
It's a journey, and it's got its challenges.
Yeah.
But it's also a journey that's full of, crazy possibility.
I'm so glad we're on this journey together.
Me too. And we're glad you're here with us. That's it for today's deep dive.
See you next time.
Into the incredible world of enzymes and machine learning.
Stay curious, everyone.
We'll catch you next time.